Welcome back, everybody. We hope you're doing fine. Before we begin, I just wanted to give you short messages and a brief repetition of where we ended last week and where we are going to head today, and what are the kind of ingredients which we need to include in the codes. So to quickly remind you of where we started last week, we started to look at the expected value of the energy as a function of the variational parameter. And then what we wanted to do is actually to find the best possible variational parameters with very few Monte Carlo iterations. And when we have these optimal parameters, the basic idea is that with these parameters, we are going to launch the large-scale calculations and then obtain the expected value, which we will process later in a statistical data analysis. So what is coming now is first the implementation of methods to find the optimal parameters, and that leads us to what is normally called gradient methods. Some of you may be familiar with a method which is called Newton-Raphson, which is a method to find the optimal or the zero or the roots of a function. But basically the methods which we're going to look at, they're going to be perturbations of this basic approach. For those of you who have taken a course in statistical learning or machine learning or similar topics, you will have encountered much of this formalism. And the main difference now is that the function you're going to apply these methods to is the expected value of the energy as a function of the variational parameters. Now, gradient methods, in particular also methods like the conjugate gradient methods, steepest descent methods, stochastic gradient descent methods, and so on, are widely popular methods in mathematical analysis of problems and optimization problems. And the field of optimization is a huge field in mathematics. There is as we mentioned last week, there is an excellent textbook by Boyd and van der Berge, which is called Convex Optimization. And you will also find it in the list of textbooks which we have in the GitHub address. There's a set of slides, and as I write here, there's something like 300 pages, which essentially gives an overview of the course which is being taught by Boyd and van der Berge. This is an excellent set of lectures. So if you wish to dive a little bit deeper into the field of convex optimization, this is a very good starting point. There's also a video on the conjugate gradient methods, which is one of the kind of standard basic methods for finding, let's say, the root of functions. Now, in our case, what we are going to do is actually to take a top-down view first, as we always have done, and we are going to look at what we need to program. And besides the simple case, we are going to implement this method, which is called the steepest descent. And the steepest descent method is perhaps one of the simplest possible ones which we can implement, or it's often also called the gradient descent. Sometimes there's a name confusion. The method which you will see implemented is the simplest possible approach, which people normally label as the gradient descent method. And for those of you who have taken a course in machine learning or statistical learning, you have met this method many, many times. So there is a simple Python code in the lectures here, which I'm going to go through first. And then we are going to go back and look more at the mathematics of gradient methods. But from an implementation point of view and the things which we need to have in the code, these examples which you will see now, they contain the essential things which have to be programmed. So then we're going to move on, as I said, to mathematical descriptions. So this is a kind of approach. First, we look at what we need to program and how we can implement it. And then when we're done with that, we are going to dive more into the mathematics here. So feel free to ask questions. I mean, unmute yourself or place some questions in the chat if you have some. The main aim with this part of the project is actually to find the optimal value for the variational parameters so that we only use some few Monte Carlo cycles. As we discussed last week, if we were to run the Monte Carlo evaluation for many variational parameters, so suppose we have 2 types of variational parameters and we have 10 values for each, you would end up having to perform something like 100 full-fledged Monte Carlo calculations. And if every calculation is something like 1 billion, consists of 1 billion Monte Carlo cycles, it means that you will have to run something like 100 times 1 billion Monte Carlo cycles. And then you're going to plot the expected value as a function of these 2 variational parameters in order to find the minimum. Now, the idea now is to get away with some very few Monte Carlo cycles in the beginning of the calculation. And then when you have found the optimal values, that is when you will just run one large-scale Monte Carlo calculation. And to achieve this, we are going to look at methods like steepest descent, conjugate gradient method. And you will see that the conjugate gradient method, which is a kind of gold standard among these gradient methods, is less efficient if you have many parameters. For the case we are looking at now, with only 1 to 2 parameters, one could even think of implementing the conjugate gradient method. However, you will find that the simplest possible gradient descent method actually does a pretty good job. You could think of implementing a steepest descent and other methods like stochastic gradient descent, or you could even use a standard Newton-Raphson method when you have few parameters. And we will come back to why when you have few parameters, it can be useful to actually run with more complicated methods. So as you will soon see, the conjugate gradient method and the steepest descent, they are methods which require that you calculate a second derivative of the function you want to evaluate. And this second derivative is often described by a matrix, which is called a Hessian matrix, and you have to invert that matrix. So if you have many parameters, this matrix blows up in dimensionality. Furthermore, the second derivative of the expected value of the energy becomes quite complicated and will require many more integral evaluations. So there is a kind of compromise here where you are going to compromise with numerical accuracy against what is efficient to do numerically, which means the number of floating, basically the number of floating point operations you're willing to spend on the problem. We can easily use Newton methods here, and we are coming back to this. The implementations, which you will see in just some few minutes, they use something which is called the Broyden-Fletcher method, which is a variant of the Newton method, in addition to a standard gradient descent method. So one of the things we did last week was to look at a very simple case where we look at the harmonic oscillator in one dimension, which is the system we have been looking at. And in this specific case, we can compute the local energy. We have a simple analytical formula. We can then integrate up, and then we get an exact energy as a function of the variational parameter alpha. So if our Monte Carlo calculation is set up correctly, this is what we should get for the energy, or the expected value. Then you can easily take the derivative of this quantity. And if you're comparing your numerically calculated derivative with the analytical formula, you should actually get what we see here. And you have a second derivative, which is always positive, since this alpha is a positive parameter, and we have alpha to the power of 4, which means that this is actually a convex function. So we have a minimum, and in this particular case, we have a global minimum at alpha equal to 1, as you have seen when you have been running these calculations. So I hope you're not getting annoyed if I repeat some of these basic features of the tests, which we can implement in our code using the harmonic oscillator. the harmonic oscillator is extremely useful because many of the integrals we end up evaluating have simple analytical expressions, like in the case here with the local energy and the expected value of the local energy. Now, one of the things I gave you as an exercise last week was actually to derive the local energy for the harmonic oscillator, which you have done in order to set up your program, and then find the optimal value, and then repeat the steps for n bosons. And this is essentially what you're implementing as a kind of a test in your code. So if your code is running correctly, these elements which you see here should actually be in your code. And then you can also optimize the variance. You have an analytical expression for the variance in this case. This is also a quantity which you could compare your numerical results with. And then in computing the derivatives, the quantity which we need to set up now is the derivative of the local energy as a function of the variational parameters alpha. And we defined two quantities last time. So one is the derivative of the local energy, which we want to optimize. And then in order to calculate this quantity, we needed also the derivative of the trial wave function with respect to the parameters alpha. So remember now that the parameter alpha enters the definition of the trial wave function. So when we take the derivative of the local energy, we're actually calculating the derivatives, amongst other things, of the trial wave function. So when we did that, what we ended up with is a total expression for the derivative, where I put this bar on top here to indicate that this expression here is now the derivative of the local energy with respect to the variational parameters. And in our case, we have now to evaluate three integrals. So this becomes an integral which we have to evaluate, where we have the derivative of the wave function divided by the wave function. And this is something we can translate into the log, the derivative of the log of the wave function. And that has the potential, since our wave function is often given by a product of exponentials. And when we take the log, this has the potential to actually simplify the calculation of this quantity. So this quantity with a bar on top is the derivative of the wave function with respect to the variational parameter, as you have seen here. So this is a kind of strange notation with this bar on top of it, but this now represents the derivative of the wave function. And then we can then calculate the expected value of this quantity multiplied with the local energy. And then we need also the expected value of this trial wave function and its derivative multiplied with the expected value of the local energy. So the last thing, this quantity which you see here, the expected value of the local energy, this is something which we have already. Then the exercise which you were given last time was actually to convince yourself, when you use the hermiticity and you use the chain rule to calculate the hermiticity of the Hamiltonian, and you use the chain rule to calculate the derivative of the expected value of the local energy, you should get this expression here. And this is the one which we need to program. So what I want to do before we start with anything is actually to run through this Jupyter notebook, and then we're going to go back to the mathematics. So there are two code examples which could serve as examples for your own program. So let's do that and go back to the Jupyter notebook and take a look at what we need to program now. So here I have added a new item to the program, which we have been discussing throughout the lectures here. So if you scroll down here, you will recognize many of these topics. Now, in this particular case, what I have is a system of two electrons moving in a harmonic oscillator well and interacting with a Coulomb interaction. So it's not exactly the same as we are doing in the project number one. It's a slight modification, but if you look at the harmonic oscillator case, that's identical to what you are implementing. So again, what you will see is a trial wave function where we have the position of one particle, the position of the other one, but we need to calculate the relative distance between the two particles. And this is given by this variable R12. So the wave function depends on two parameters, alpha here and beta. Alpha is the dominating variational parameter. Beta is more kind of fine adjustment, which happens to occur in the correlated part of the wave function. And the correlated part of the wave function is the exponential of the relative distance divided by 1 plus the parameter beta times the relative distance. And then it returns simply the exponential of the product of two harmonic oscillator wave functions and multiplied with the correlated part, which is now given by this deno here. And then the local energy has an analytic expression, which I've coded here. Now, the next thing which we need, and when you go back to the expressions which have to be coded, so if you go up a little bit, if you look at these expressions here, you could use, if you're programming with Python, you could use automatic differentiation and calculate the derivative of the expected value of the local energy. But in this case here, I'm now calculating the derivative of the trial wave function with respect to the parameters alpha and beta. So this is W of f there is actually wave function derivative. And what this object returns is the derivative of the wave function. So if I go up a little bit, what you will find then is that this quantity, which is you see here, is now this wave function derivative with respect to the parameters alpha and beta in our case, but you can write this in a more generic way in terms of a parameter alpha here. By the way, there's a sign here which shouldn't be here. I discovered there's a typo. So this larger than sign should not be there. It's actually deep psi of as a function of alpha only. So this symbol here is a typo. Sorry for that. This I didn't see that before now. And then when we have that derivative, we need to evaluate this integral, and we need to evaluate these two integrals which you see here. And essentially the code, what the code is actually doing is to take the analytical expression for the derivative of the wave function ansatz with respect to the parameters, and that's what it returns here. So derivative with respect to variable 0 is actually with respect to this variable alpha, and variable 2 is this variable beta. Then we have the quantum force, which we discussed last week and the week before, which we include in order to perform the important sampling step. And then there's a function which we call energy minimization. And in this particular case, what I'm doing now is I'm using less Monte Carlo cycles. Now, this leads to a small problem, which we need to think of. And that problem deals with the fact that the integrals we are evaluating in the calculation of the derivatives of the expected value of the local energy, they may be very sensitive to the number of Monte Carlo cycles which we set up. So remember now that when we look at these integrals here, these are expected values, and clearly the more Monte Carlo cycles we can plug in here, the more accurate will these values be. And since we are calculating the difference of two values, they can be very sensitive to cancellations due to stochastic errors. So in this evaluation process, we have a weak point which we have to keep in mind. Now, in this specific case, what I'm doing now, I'm starting everything randomly, so it's a stochastic calculation, and I'm setting up just 10,000 Monte Carlo cycles. You can clearly augment that if you want to. Then what comes are the same basic steps as before. Old position, new position. We calculate the old quantum force, the new quantum force. We set up the expected values of the energy, delta E. We have the energy derivative, which is the new expected value. we need the integral of delta psi, which is this additional integral which we have, which is actually, if we go back, if you look at this integral here, that is an integral which I labeled delta psi. Then we need another integral which includes this function multiplied with the local energy. So if we move down then into this function, you will see now that we are updating these variables because we need the energy derivative, we need the this integral, and we need this next integral here. So if we scroll down, we have the standard metropolis testing, which comes in here. And we find the new positions. We update the quantum force. But now we have new integrals, which we need to evaluate. So one thing which I want to have is obviously the local energy. And we have the derivative of the wave function. So this function, derivative wave function ansatz, goes into this delta psi. And then we have another integral, which is a derivative of the wave function times the local energy, which now contains the derivative of the wave function multiplied with the local energy. And this is being added up. And then I need the integral for the local energy, and I need the integral over the wave function. So these quantities which you see here, these three quantities, these are the three new integrals which we need to evaluate. And then I'm now running over the Monte Carlo cycles, and you can see now that there's a final function which is called the energy derivative, which now contains the first integral minus the next integral times the integral over the local energy. And these are the quantities which you now need to think of adding to your program. In this particular case, the exact energy in atomic units is given by 3, the number 3. So the correlated case should now give us an exact answer if we have the exact wave function, which is equal to 3. I start with a guess with the variational parameters here. I set up the derivatives. And in this case, what I've done now is to compute a number of iterations, in this case 50, and I have not made a very intelligent code here. So what would be a more intelligent way of doing that is that if your gradients are getting smaller than a certain amount, then you would stop calculating. So here I'm just testing if I get away with something like 50 iterations. And what I'm implementing here is the method which is called gradient descent. And we are coming back to what this method looks like. For those of you, again, who've taken a course in machine learning, you have seen the way you calculate these derivatives using gradient descent. In this case, we are using a parameter which avoids us makes so that we don't need to calculate the second derivative of the local energy. And this becomes a parameter which in machine learning is normally called the learning rate. For us, it becomes a parameter which now makes life a little bit easier when it comes to the calculations of higher derivatives. And we are calculating the gradients in terms of this parameter times the gradients, which are now given by these derivatives. So I have one variable, which is the alpha gradient, and then I have the beta variable gradient. And these are the two gradients which I want to drive to 0 if I have found the correct roots of my function. So you can see now after 50 iterations, these are the values of the optimal parameters alpha, and this is the value of the optimal parameter beta. This is the value of the energy I get after these steps. And you see now that the exact energy is actually 3. I'm only running 10,000 Monte Carlo cycles. So if I were to increase the number of Monte Carlo cycles, I would actually get even closer to 3 here. So that means that the trial wave function I have is a pretty good estimate. And you see now this is the derivative of alpha, which ideally should be equal with respect to alpha, which ideally should be 0. And this is the derivative with respect to the function beta, which also ideally should be equal to 0. So you see now that this kind of brute force way of setting up the derivative gives something which is reasonable, but it still has a derivative which is not exactly equal to 0. So we can improve upon this very simple approach. Now, the thing I want you to observe is that the thing which will not change is the calculation of these derivatives. So you may use different methods to find the roots. That means where the derivative of the local energy is 0. This is the function we want to find the roots of. But you would need to calculate these three integrals. And these are given by the functions which you see here. So the derivative wave function ansatz, we calculate the integral for the derivative of the wave function. We have the local energy integral, which we have been evaluating. So this term which you see here is what we have from before. And then you can set up your favorite scheme. And in this particular case, we are using what is called the simplest possible approach, which is called gradient descent, with no fine-tuning of this so-called parameter eta. So this parameter eta can actually be fine-tuned in order to give better gradients. But you see now that it's functioning decently well. So we are getting an estimate for the energy, which hopefully is at the minimum, where the minimum is given by these values of 1 close to 1 for alpha and 0.31 for the parameter beta. Now, there is a famous algorithm, which is a simpler or what we might call an approximation to Newton-Raphson methods, which functions very well when you have a low dimensionality or in terms of the variational parameters. And this is called Broyden's algorithm. And we are going to discuss parts of that next week. Here, what I'm showing to you is the implementation of Broyden's algorithm using scientific Python. There is a similar implementation of Broyden's algorithm, which is discussed a little bit below in the lecture notes using C++. So this is a famous algorithm. It's often shortened to BFGS. That's Broyden, Fletcher, and I never remember what GNS stands for. These are two other characters, and I always have to revisit it. The function which you saw previously is the same as we are using with the Broyden-Fletcher algorithm. But in this case, what we are doing now, besides setting up the derivative, so there is a function for the energy derivative, which receives an array with the variational parameters. And the same as we saw before with respect to the metropolis test, importance sampling, all the ingredients you have developed, they're included here. And what is also added here is the evaluation of these three integrals. So the thing you need to set up now, or to think of setting up, is the evaluation of these integrals which are needed to find the optimal parameters alpha. So in the usage of this method, of the Broyden method, so what I'm doing now, I'm running through the Monte Carlo machinery, and I'm performing my optimization. And you can see now that the way I would call this is to have a function energy, which is here, and that computes the actual energy. It takes in, so there's a minimization function in scientific Python. I send in an array with the initial values for my parameters, 0.9 and 0.2. I call this function minimize. That needs a function which sets up the calculation of the energy. So that's why I have the function up here, which is called energy. So it needs that, and it needs a function which returns the derivatives of the energy. So this specific function, if you want to use it either in a C++ variant, Fortran variant, or scientific Python, it needs a function which sets up the energy, and it needs a function which sets up the energy derivative. And here I put a tolerance of 10 to the minus 4. And you see now that the I may not have achieved the correct value. It gives me a function value after 6 iterations. So this is a pretty efficient method, which is pretty close to 3. I haven't estimated the standard deviation. And then it gives me the parameters of 0.98 and 0.4111. So with these parameters, I could now start attempting to calculate the expected value of the local energy with a large number of Monte Carlo cycles. So that is actually the next step. So what this iterative procedure gives me is the optimal parameters, which I'm then going to plug in a calculation of the final local energy so that I can perform a statistical analysis of my results. So this is a kind of overarching view on what we need to do. So what I wanted to do now is actually to go back to the basic mathematics of these kind of methods and just remind you again what we need to program and what we need to have in the program in order to move on to the next step, which is the statistical analysis of the results. So when we run the large-scale Monte Carlo calculation, that is when we're going to produce data for a statistical analysis. And the statistical analysis is going to contain an evaluation of quantities like the standard deviation, so that we can assess that the standard deviation we are producing is something which we believe in. So at the end point, which we are going to deliver, is the expected value of the energy plus minus a standard deviation. And this is something which we can do with something which are called resampling methods. So I hope you can see the kind of overarching view here. And this kind of program is more meant to give you a bird's overview of what you now need to implement numerically. So there are 3 integrals which you need to plug into your code. And you can look at this example here as a kind of guideline on what you need to set up. So any questions so far? Is everything clear? So feel free to unmute yourself or just put a question in the chat. Okay, if there are no questions, what
excuse me.
Yeah.
I was wondering, the energy was lower than the exact energy.
Yeah.
Is that
you have always to give a standard deviation. So your energy will always be computed within a standard deviation. So in this case, the standard deviation is missing. And if you rerun this with a new set of initial parameters, you may get a value which is not exactly this one. So we could try this again and just rerun it. And then you will see that, so it takes some time, but then you will probably get something which is perhaps closer to 3 or slightly above or slightly below. But the expected value, you will never present only the expected value. So in this case, you actually got something which is slightly lower. And you see also this optimal value changed. So everything will depend on the number of iterations you're doing. And you see also in this specific case, the desired error is not necessarily achieved due to precision loss. So we could change like something here. We could set a tolerance, which is smaller. That will normally lead to less iterations and a slightly different value. Now, what you're going to see is that every time you run this calculation, since you're evaluating these integrals stochastically, you see in this particular case, the values changed a little bit. And now we have a value of 2.9966. So you're getting closer to 3.0. So the results will depend on your calculation, the seed which you give to your random numbers. It will depend also on the number of Monte Carlo cycles you want to invest in every such calculation here. So in this case, we're just doing 10,000, which means that maybe this accuracy is not optimal. So when we calculate the energy derivatives and evaluate the energy, we have a limited number of Monte Carlo cycles. So what many people do then is that they would rerun this machinery in parallel and then take the average of all the possible optimal values of alpha and beta. We are coming back to this towards the end of project number 1. But keep in mind now that there is a missing item, and this is a very important missing item, and that has to do with the correct evaluation of the standard deviation. And that's something which we need to evaluate. And that is going to be the next element we will have to plug into our calculations. So typically what you will see is that the standard deviation will be something which is going to hover around the third and the fourth point after, no, the fourth decimal after the, no, the fourth point decimal after the, no, the value after the decimal point. Sorry, I'm just messing up now. So I hope that answers your question here. So when we run Monte Carlo calculations, there is always a standard deviation. And that's going to be one of our next elements which we need to implement. So I'm going to stop sharing here and switch back to the whiteboard, because now I just want to go through some of the basic mathematics here so that we know what we are going to do and why we are going to do what we are doing. So let me quickly remind you of the basic elements which we need to set up. Can everybody see my whiteboard? Is that fine? Okay, so what we need when we are setting up these gradient methods, so let's just set up the basics here. And let me remind you of the elements which we need to evaluate. So one of the elements which we need is obviously the expectation value of the local energy, which we have written as a parameter of this alpha. So this is the integral which we already have. So this is given by a d of r, and r is an element in the given domain. And we have the probability distribution. And I'm putting a vector alpha to indicate that this is a quantity which may contain more than just one variational parameter. So this is one of the quantities we need to evaluate. We need also to evaluate the expected value of the trial wave function. So let's just bring that up. So another integral which we need is the integral or the expected value of the trial wave function psi t with respect to d alpha, and this is divided by the trial wave function itself. So there's a new integral which we need. And then this is just a formal way we write it. And this derivative is normally written as a d of ln of psi of t with respect to the parameter alpha. And finally, the next integral which we need to evaluate in order to find the derivative of the local energy is the integral of what we wrote as a d ln of psi of t of d alpha multiplied with the expected value with the local energy. So these are the three quantities which we need. I don't need to set up the integral because that should be pretty obvious. So if we are dealing with a standard gradient method, irrespective of the type of gradient method, what we are looking after now is an alpha optimal. So opt for optimal. And this is going to be the minimization over alpha, which is now in this set of parameters alpha. So we have m alpha values, and then we need to optimize the derivative on or the local energy, which then means that we need to evaluate the derivative of the local energy. So one of the simplest possible methods which we are going to look at now is based on an approximation where we introduce something which we call a learning rate. So the simplest possible method which we can implement and this is a simplification of the standard Newton-Raphson method. Implementation. This is now given by this iterative process. So where we have alpha, and K here stands for a given iteration. So this is an iteration. And this is given by alpha, calculated at the previous value, minus, and now we have the gradient. And in this specific case, we replace the second derivative of the local energy with a parameter. So this is just a parameter which we can tune in order to get the best possible evaluation of these parameters, of the parameters alpha. So we need the gradient of the local energy. So this is the expected value. And then I'm just writing this EL. And this is evaluated at alpha at the kth iteration. So we would evaluate the local energy at a given set of points alpha, and then we would get the gradient. So it means that if we now are looking at a plot of this, and we reduce the problem to one dimension in alpha, so we have only one parameter alpha, we will get something like this. So we have alpha here, we have the optimal alpha, this is the value we want to find. We need then the gradient. So we could start here. So this would be alpha 0. We would get to the next point. We would have an alpha 1. And this would just continue all the way down here and hopefully as fast as possible. And this will be our alpha of k, the final value, which is now the value which is going to be the optimal one. So this alpha 0, which you see, this specific parameter here, is normally our starting point. Now, this starting point is often given by our guess about the system. So, and that's why when you're running this Monte Carlo calculation, this is why the harmonic oscillator is so important. So we have a system which is given by particles which are being trapped in a harmonic oscillator potential. And then they interact either with a strong interactions, it could be a weak interaction. But in most of these approximations, what we are assuming is that the harmonic oscillator part is the driving part of the Hamiltonian. And since this is going to be a weakly interacting system of bosons, what happens is actually that the energy will not deviate that much from the standard harmonic oscillator. So that means that the harmonic oscillator serves as a very good starting point for making this guess of the parameters alpha. And we know that from the non-interacting case, that means no interaction at all, that the optimal parameter alpha should be equal to 1 with the ansatz we have chosen for the wave function. So you would typically stop this process. This is an iterative process. You would then stop when this parameter alpha of k plus 1. So we are typically looking at the norm 2 of these parameters of k. So 2 here stands for the norm 2 is less than some given number delta. So this delta could typically be in the range of, let's say, 10 to the minus 8 to 10 to the minus 10, just to give you an example. So it's actually you who sets the tolerance. In these examples, which I run before, I put a tolerance to 10 to the minus 4. So that depends, it's something which depends from case to case. So this parameter, which you see here, for those of you who are familiar with the machine learning algorithms, this is called the learning rate. Now, in our case, this is just going to be a cheap way of replacing the second derivative of which appears in Newton-Raphson's method. So after the break, we're actually going to remind ourselves about the Newton-Raphson method, which is the starting point for many of these methods. And the reason why we don't want to use the full Newton-Raphson methods is because we need to calculate, well, since we are finding the zeros of the gradient, that means that this learning rate is going to be proportional to, or actually equal to, the inverse of the second derivative of the local energy. And we don't want to evaluate the second derivative because that involves even more integrals. So if you think the first derivative is involved, the second derivative involves even more integrals, which we have to evaluate stochastically. So that's why we are trying to use methods which mimic what the Newton-Raphson method is doing, but we want to avoid evaluating second derivatives, because in our case, that is going to lead to more integrals to evaluate. And since these integrals are evaluated stochastically, it means then that we will carry with us an error which can condition the final results for the second derivative and the first derivatives as well. So our results will be sensitive to the way we evaluate integrals. And these approximative methods, like the plane gradient descent, they are variants of the Newton-Raphson method, but without having to evaluate the second derivative. This Broyden's method is actually a method which attempts at evaluating the second derivatives and makes an approximation to the second derivatives without calculating the full second derivative. And then there is a whole plethora of methods which allows you to evaluate this kind of gradient stepping in better ways or more improved ways, which take into account more information about the second derivative. So we're going to take a small break now, and I'm going to stop the record, but I'll pause the record. Now, what we want to do now is to give you an overview of important gradient algorithms. So the kind of methods which we are going to discuss now are methods like what is called the steepest descent. So this is not in the sequential order. I'm just listing the algorithms. We will discuss what's called the famous Newton-Raphson algorithm for finding the roots of a function. We are going to look at an algorithm which is perhaps the kind of golden standard in this kind of gradient methods, and that's called the conjugate gradient descent. We have the plane gradient descent method. As you can see here, there's a family of different types of methods. So plane gradient descent. And I'm going to highlight that one because that's one of the simplest possible methods which we can implement. And we will see how we can do that. Actually, the demonstrations which I showed you in the previous lectures were based on the gradient descent. That was one of the demonstrations. And then we are going to look at approximations to the Newton-Raphson scheme. And in that case, we have something which is called the Broyden-Raphs, the Broyden-Fletcher, etc. algorithm. So this is called the Broyden algorithm, Broyden et al. This is one of the approximations. And what I wanted to motivate is why we end up doing this type of approximations. And as I said, one of the things we want to avoid doing is to calculate the second derivative of the local energy. So there's a plethora of methods, and these all belong to what we normally call convex optimization problems. So the class, and we're actually assuming that the function we want to optimize is a convex function. So the class of convex optimization problems. And if you dive into that textbook, which I linked to at the beginning of the lectures, optimization problems, there is another class of methods which we can also think of implementing, and which are widely used in machine learning algorithms. And I forgot to mention that here. So this is normally called stochastic gradient descent methods. And people have applied these methods in Monte Carlo evaluations as well. So the local energy, which you have seen now, and its derivative, derivatives which we can also evaluate using something which is called a stochastic gradient descent. So the overarching goal is that we want to find the set of parameters which minimize the local energy without having to run through calculations, extensive Monte Carlo calculations where we map out a set of variational parameters and then try to find the optimal values. So the basics of what we're going to look at now is the following. So we, in the notation which follows, I'm going to replace the expected value of the local energy with just a simple function here. So I'm going to replace that one with a function f, which depends on some variable x. So this is just to simplify life here. And the derivative, or the gradient of x, of this function f of x, is something which I'm just going to refer to as a gradient of f of x, like this. And what we want is this quantity to be equal to 0. That's the function which we want to optimize. So what we want then is actually the roots of this function here. Now, if you now look at a very, very simple example, so let's suppose we have a function which is f of x. Just to quickly remind you of the things you may have seen before in mathematics courses, then we know that the derivative in this particular case is just given by x. And if we make a plot here of this very, very simple function, we would have, if we take x equals 0 here, and then we plot f of x equal to 0. So we have f of x here. Then we would have something like this. This is our function, which we have centered around 0. And we know that if I were to start here, in this specific point, if you look at that one, that is a point where I have x larger than 0. That means that the derivative, f of x, is also larger than 0. And when we now are searching for the optimum, then we need actually to move to the left. This is pretty obvious, right? So if I were to move to the right, I would just go to larger and larger values. So I would like to move in this direction here. So we would like to move to the left. So how we move depends obviously on the value of the derivative, which in our case is going to be a multivariable function. So in our case, this is going to be the gradient, which we are looking after. Now, if you look at the case when x, so let's just highlight that one here. So if x is less than 0, then clearly the derivative f of x is less than 0. And f of x is then decreased So we want to decrease it till we reach the optimal value, is decreased by moving to the right. So this is some of the basic kind of things which we can develop from an intuitive picture. We have different types of problems which we will encounter. So ideally, we would like to have a function which looks like this. So we have an alpha optimal. So in this case, we have a minimum. But we could also have a function which has a maximum at that point. And in case we have a function which has a maximum value, like this, so this would again be the point where the derivative is equal to 0. What we normally do then is that we will put a negative sign in front of it in order to obtain a minimization problem instead of a maximization problem. In general, the functions which we are going to look at, they are going to be functions which are convex. And we will see that from the second derivative, that the second derivative is normally positive. Now, one thing which causes problems for us in these calculations is the case where we have so-called saddle points. So we could now have so I'm just plotting the function f of x here, and we can have some delicate points where we would have something like this. In this case as well, the derivative is equal to 0. So you would have an f of x equal to 0. And this is normally called a saddle point. And they can cause problems in the optimization and the search for the optimal values, because you can be stuck in a saddle point for quite some time because the derivative is essentially 0. And you may not know that because you're dealing with a multivariable function. Now, the general case, which we will encounter, and now I'm just making these plots in one dimension because that's what's the easiest to visualize. But in general, what we have is a multivariable function. And we can easily end up in a situation where we have a function which looks like this. And then we can have something like this, and something like this, plateau, and just a complicated type of function. So we could have a function, a point here, which would be our global minimum. And that's the point we normally want to reach. So this is the plot of f of x. We may have points like here, which would be a local minimum. We can have local minima, which are shallow local minima. We would have points like here, which would be a saddle point. This would typically be an example of another minimum, which we would call a shallow minimum. And so on and so on. And ideally, we would like to reach the global minimum, but when we do the searching for the derivatives, we may be stuck in a point like this. So that means that when we apply many of these gradient descent methods, there is the obvious risk that we will be stuck here and the derivative is going to be 0. And we will never be able to tilt over to the next points and then just move down and perhaps up this point and then down to the final point which we would like to be at. So we can easily be stuck in a local minimum. And since these functions are often multivariable functions, it can be difficult to assess whether we are in a global minimum or a local minimum. Now, another quantity I want to introduce to you is now the second derivative of this function. So the second derivative, d of f, with respect to the variables x of I and x of j. This is a function which now is called the Hessian function, and it's going to define a matrix. So this is a matrix element of the Jacobian, And this Jacobian is normally called, this second derivative in our case, this is called the, so this matrix elements of what you normally will find in the literature, something which is named as the Hessian matrix. And that's why I'm putting an H on it. We are coming back to this. Now, in most cases, this matrix is actually a positive definite. That means that all eigenvalues are larger than 0. And that leads to a convex optimization problem. So in most cases, this matrix H, where the matrix elements are Hij, this matrix is positive definite. And this leads to a case where so this means actually that all eigenvalues of that matrix are larger than 0. If it's semi-positive, if it's semi-positive definite, then the eigenvalues are larger or equal than 0. So the matrix can also be semi-positive definite. If it's not a positive definite matrix, then we are not having a convex optimization problem. It's larger than 0. And this leads to, so I'm just stating this from gradient optimization theory. So this leads to a convex optimization problem, which means that there can be both global minima and local minima. So this Hessian matrix, which is defined by the second derivatives of the function, they enter the standard search for the optimal parameters. So let's look at how these things come by here. So what we're going to look at now is a Taylor expansion of the function which we want to optimize. Taylor expansion of a specific function, and then we will see how Newton's method actually comes in. So if we now look at the Taylor expansion of this function, where I keep now this vector notation. So I have an f of x. And if we now stop at second order in the Taylor expansion, we can now write an approximation sign. So this is going to be given by an x0. So this is the point we are expanding around. Then what I have, and since these are vectors now, I have to be a little bit careful. Remember this, the function is a scalar. So we have a vector here. So this is just a plain Taylor expansion. This is a transpose of this vector multiplied with a gradient. So G is now the gradient of this function f of x. So f of x is something which I'm just going to label with a G here. So this is the first term. And then the next term here now contains my, in vector notation here, it contains the second derivative of the function f, which we define to be equal to this Hessian matrix. So what we end up with then is an x minus x0 transpose, and then this is multiplied with a Hessian matrix, and this is again multiplied with x minus x0. Now, what we could do now is to make an approximation here. So we could, in this equation which you see here, we could now say that x minus x0 is approximated with a parameter gamma multiplied with a gradient. So I'm just going to write it like this. So we are now approximating the function with simply just the difference between x and x0, the two values, with the gradient times some parameter. So gamma is a parameter. So that means that I can rewrite my Taylor expansion, where I've now made an approximation for the difference between x and x minus x0, which is now given by f, and now I have a f of x0 plot, and it gets a minus, because what we are doing now is that we have a term which we rewrite. So this actually what we are going to have, sorry, x minus x0 is going to be minus gamma times g. So I'm going to have a minus gamma, and then I have g transpose times g, the gradient. And then I have in addition plus 1/2 this parameter gamma squared of g transpose times h times g. So this optimal gamma is something which I'm going to get now when I'm going to calculate the derivative. So if I now calculate the derivative with respect to gamma, optimal gamma is now obtained by taking the derivative with respect to this parameter gamma. And if I now look at the expression which I have, so I want to optimize this function f of x in terms of this parameter gamma. And that means that what I get then, so I want this to be 0. And when I take the derivative with respect to gamma, I get the following expression then. So I get a g transpose times g, which is simply equal to 1/2. So I had gamma squared, and the derivative of that one is obviously gamma. So I get gamma multiplied with g transpose times h times g. And that means obviously that gamma is equal to this optimal quantity. Gamma optimal is equal to the vector g transpose times g divided by g of h times g here. Now what you see is that this quantity here is actually given by this second derivative matrix multiplied with a vector with a gradient. This kind of step which you see here is going to lead to what we normally call the Newton-Raphson, not the Newton-Raphson method, but the steepest descent method. So later you will see the evaluation of this optimal value for this parameter. Now, if we now go back to Newton-Raphson's method, what we have in that case is an iterative scheme where we have a k plus 1, and this is an iteration k plus 1 using the values from the previous iteration. So when we want to find the gradient to be equal to 0, this is going to be given by minus, and then I have 1 divided by the Hessian matrix, calculated now at a value x of k. So I'm putting f of x of k because h is a function of f, and this is multiplied with the gradient of f of x of k. Now, one of the things which we did when we made the approximation above here, if we now look at the approximation here, we assume now that this x minus x0 is given by this gamma times the gradient. And if we now look at what we have found here, is that we have a variable gamma, which is now given by the inverse of this Hessian matrix. So what we have is actually something which we could have written as k plus 1 is equal to x. So this is a modification of the Newton-Raphson method, which goes like minus of gamma multiplied with the gradient of x of k. Now, what we did here, this leads to what is called the steepest descent method, standard steepest descent. And we are going to look at the analysis of that method a little bit later. The standard gradient descent method, instead of calculating this parameter gamma using the optimal value, what you would typically do then is to assume a set of values for this gamma here. So as I said, the thing we want to avoid is to evaluate the inverse of this Hessian matrix, which now depends on the various derivatives. You can find an optimal value, which is given in terms of the gradient, divided by the gradients multiplied with the Hessian matrix. So the Hessian matrix needs the evaluations of the second derivatives. And the second derivative of the local energy is just simply a messy function. So the standard gradient descent, which is the simplest possible method, assumes that gamma can be seen as a parameter, can be seen as a tuning parameter. And you would tune that one so that you actually get the optimal reproduction of the zero of the local energy or the function you want to evaluate. It can be seen as a tuning parameter. That means that since you don't want to evaluate the derivatives of the local energy, you don't want to evaluate the second derivatives, which leads to a complicated set of integrals to evaluate stochastically. You could then think of choosing gamma as a set of parameters which you would use in the calculation of the gradient descent method. So you could choose a set of variables which, or trial values, which goes from 10 to the minus 5, 10 to the minus 4, 10 to the minus 3, and so on, up to, let's say, 10 to the minus 1. If you make it too large, you will be jumping in and out of the region where you want to optimize the function. If you choose it too small, you risk to remain in the same position and barely move after a certain number of iterations. So the standard gradient descent is a very simple method to implement. And this is typically the method which we would normally just advise you to try out in the beginning when you're setting up the derivatives. And then you would play around with different values of this parameter gamma and find the one which gives the best result. There is an improvement to this parameter when you're dealing with multivariable spaces, which is called stochastic gradient descent, which we will also discuss next week. And but the simplest possible implementation is the so-called gradient descent method. And I would advise now, when you're setting up the program, in the first approximation, just use the simplest possible gradient descent. Use, and we are going to call this for GD, just gradient descent with a parameter gamma chosen between something like 10 to the minus 4 to 10 to the minus 1. And then just see that your derivatives, the calculation of the derivatives, is functioning correctly. So it's moving the way you want it to move. And then when you have that, you can move on to more sophisticated methods. So the next step could now be the following. Next step. So that could be either including what's called a stochastic gradient descent, which we will discuss a little bit more next week. Or you could now include this pseudo Newton-Raphson method. So we would then typically include a method like this Broyden et al., which is a kind of pseudo Newton-Raphson methods. So it's a Newton-Raphson based method. But it's not the full Newton-Raphson method. It's actually a method which tries to estimate the value of the second derivative of the local energy. So these would be the kind of steps which I normally would recommend in the optimization of the variational parameters. So remember now that the kind of overall picture which we want to is to find the optimal parameters with as few Monte Carlo cycles as possible, so that we can then evaluate the function for the expected value of the energy with as many Monte Carlo cycles as possible. That is typically the production run, which we want to set up. So everything is now based on this simple Taylor expansion of the function we want to evaluate. We want to optimize the derivatives. That's the function we want to set up. So that means that we can derive the optimal value for this parameter gamma, which is going to lead to what's normally called the steepest descent method. The cheapest possible way of doing this is to replace the second derivative. And in our case, when we deal with more than one variational parameter, this ends up being a matrix given by the Hessian matrix, and then we have to invert the matrix as well. And we would typically replace that with a parameter which is being tuned so that we get the best possible derivatives of the function we want to evaluate. So any questions so far? This is a kind of still the kind of overarching picture of what we are dealing with. If there are no questions, what I would like to move on to now is the derivation of two very important methods, but which we are not going to use. And these methods are the so-called steepest descent, and you saw one derivation of it by calculating the optimal parameter gamma. But what we want to do now is more to look at the mathematics of these methods. So we are going to look at the steepest descent and what's called the conjugate gradient descent method, or just the conjugate gradient. So in a certain sense, this becomes a digression to what we need, but it's important to have seen these methods because they are widely used in optimization problems. And these methods, they rely on you being able to calculate this Hessian matrix. So the essence here, being able to evaluate the matrix H. Now, I want you to look at this problem from another point of view. And if we now go back to the simple Taylor expansion which we made, we can make this a little bit more abstract or more formal. So we started with a Taylor expansion of the function f of x. And this Taylor expansion gave us now, when we wanted to optimize the parameter gamma, we found an expression which is given by this trial or this gradient times this, its transpose times the gradient divided by the gradient multiplied with the Hessian matrix. That gave us the optimal parameter gamma. If we want to do that, you see now that we actually have to calculate the gradient and multiply that with the Hessian matrix. And we have to evaluate the quantity which you see in the denominator here. Now, everything which I'm doing now is something which we are not going to implement, but you could think of implementing that if you have the possibility of calculating the Hessian matrix. Now, what we are going to look at is at the problem in a slightly different way. So I'm going to replace H with a matrix A, just to make this very general. And there is a problem when we have the matrix, or the matrix with a vector squared x, so which leads to a standard linear algebra problem. So A is a matrix. So this is a matrix which we can think of dimensionality of R of, let's say, n times n. So it's a real valued matrix. And this leads to a standard linear algebra problem where we have a vector A multiplied with a vector X equal to a vector B. What we're also assuming now is that X transpose times A times X is a positive definite matrix, is larger than 0. So we are saying now that A is a positive matrix, is a positive definite matrix. And the Hessian matrix is normally always a positive definite matrix. It's a positive definite matrix. So the problem of actually solving this Ax equal to B, problem of solving Ax equal to B, this is a problem which is equivalent to the problem of optimizing, could say minimizing. When I say optimizing, we are often thinking of minimization or maximization, of optimizing the quadratic function and I'm going to use a Q in order to indicate that this is a quadratic function, Q of X, which is equal to X transpose times A times X minus, and often what people do now is that you can put in factors of 2 in different ways. You often put a factor of 1/2 here, minus X transpose times the vector B. So B is also a vector here. And if we take the derivative of this quantity here, of dq with respect to d of x, this leads to, and we want this one to be 0, that leads now to a problem which simply is ax equal to b. When we take the derivatives of a vector here, or the function with respect to the vector. So this type of problem is something which suggests an iterative scheme. And the typical way you would now start setting up the scheme here is to assume that there is a vector which you can start with, and you would typically define that as a vector x0. So what we are going to suggest now is an iterative scheme where we now have a vector x of k plus 1, which is equal to b, and where we started with an iterative scheme, and then we arrive at the final solution x of k plus 1. So x of 0 is a kind of starting guess, is a start. And then we would iterate towards the final value xk plus 1. Now, there are some important statements in linear algebra and some theorems which are extremely useful. So if this matrix A is a positive definite matrix, then what you can show is that irrespective of starting point x0, you will always reach the exact solution x of k plus 1 after a given number of iterations. So this leads to, for instance, a method which is called the Jacobi's iterative method. You have something which is called the Gauss-Seidel method, which is another way of iterating this kind of problems. But the theorem states that if A is a positive definite matrix, if that is the case, then starting with an iteration, starting with a random or any starting point with a random x0 and iterating will always lead to the exact solution after a given number of iterations. And iterating will always lead after k iterations, then I'm going to write this here, after k iterations, to the exact value within the numerical accuracy you have chosen. To the exact value. And when I say exact value, that is within the numerical precision which we have chosen. Value x, which solves a times x equal to b. And what we would typically have then is a precision which is given by x of k plus 1 minus x of k. And this is the norm 2, which is smaller than a chosen parameter. So we have chosen the specific precision to which we want to find the solution. So in the beginning here, we performed a Taylor expansion. Let's now look at the what is normally called the steepest descent algorithm. And let's derive that one and show that this actually gives us what we got when we performed a Taylor expansion and wanted to optimize the parameter gamma. So let's set up the steepest descent. So one thing which I'm not setting up here, but if you are a little bit unfamiliar with it, I could add some notes about derivatives of matrices and derivatives of vectors. So keep in mind now that what we have here is actually a function which depends on a vector and a matrix. And that means that when I take the derivatives of these quantities, I have to look at derivatives of matrices and vectors. So if you're a little bit unfamiliar with that, I can set up the basic expressions a little bit later, or just add them in the lecture notes in case you're a little bit unfamiliar with these quantities, because often in mathematics, they tend not to list some of the operations like this one here. So if this is something which is unfamiliar, please let me know, and I will add some notes about it. Okay, so if we now want to derive the steepest descent method, what we have shown now is that this q of x, when we want to minimize it, q of x minimized. Let me see now, I can't write anymore towards the end of the lecture here. Minimized. And where q of x now is a function which is quadratic in the unknown quantity x, then what we end up with is to solve this problem here. So we define what's called a residual. This residual here is defined as R, which is B minus A of X. This is the quantity we want to minimize. So after a given number of iterations, we want B minus A of X to be as close to 0 as we can define 0. So we would typically start with an x of 0, and x of 0 could just be a random vector. It could even be 0. So that means that there's going to be an r of 0, which is given by b minus a of x of 0. That means that we will also have a residual, which depends on the given iterations. And this is the quantity we want to drive to 0, which is going to be given by b minus a of x of k plus 1. Now I see that my time is over now. And what we are going to do is to derive the steepest descent algorithm at the beginning of next week. Then we're also going to look at the conjugate gradient methods, and we will try to wrap up the discussion of these different gradient optimization methods in the next lecture. So this is to be continued. What I wanted to show you is just to state the final result. So if this matrix is positive definite, what we will find is a quantity which is going to be given by these residuals, which now is going to be given by the so the optimal residual when we want to calculate it, residuals are going to involve the calculation of this quantity here, which we are calling r of k of t of r of k divided by rk transpose. So this is after iteration k. We just rewrite it in a better way. So we're going to have a function, and this is something we will derive next time. So it's the transpose of k after a given iteration. So these are vectors. So it's RT of k multiplied with this matrix A and multiplied with a vector R after iteration k. So next week we are going to derive that term, and this is going to play the same role as this learning rate. So this will now be given by this parameter gamma of k. So we can evaluate this parameter gamma at every iteration in terms of this residual. And that's the steepest descent method. And the steepest descent method involves the evaluation of the Hessian matrix. And you see now that since this Hessian matrix involves the second derivative of the local energy, it's normally something which we don't want to evaluate. And we are going next week also to look at methods which allows us to estimate this gamma of k in more efficient ways, and avoiding thereby to having to calculate the Hessian matrix A. But as I said, the simplest possible method which we can think of is the so-called gradient descent method, which we put up here, and where you simply calculate the derivatives, the gradients, and you multiply that with a parameter which you can tune. This is perhaps the simplest possible step in the development of our code. Then we can start implementing more advanced methods like a stochastic gradient descent, or we can use this kind of semi-Newton-Raphson methods like the method of Broyden et al., which makes an attempt at estimating the Hessian matrix. The steepest descent and the conjugate gradient methods, I'm mentioning them because they play an important role in these optimization problems, and you're going to encounter them. But they are useful if you can calculate the, in our case, the second derivative of the function we want to evaluate, which in our case means the second derivative of the local energy. And that's a quantity which we don't want to evaluate. So the steepest descent and the conjugate gradient descent, they are included here for the sake of completeness, but they are less efficient algorithms. So I'm going to stop the recording.